I was behind very much like I needed one involved. And this is very much. Like, oh, no. I got to one more like.
Okay, we're going to just do more practice with what we started on Friday. But I just want to kind of show these diagrams here just for us to be able to recognize when a problem is this method or wash method. So if it's this method, that means we only need one radius because there's no hole, there's no gap. But if there is a gap or there's a hole, or if the shaded region is up against, or if the dotted line is up against the curved region, even if it's touching, we still need to remove the hole, which means that we have to involve a second radius to subtract that out. So I want us to just do a quick look at these problems and just for us to categorize, is this method or is it wash method? So again, if your axis is up against a flat surface of the shaded region, it's going to be this method. Anything else, it's going to be washer method. Even if it's touching, but there's a curved region, that's going to be washer method. Okay, so number one, disc or washer. Disc, right? You see that there's no gap between the axis and the shaded regions up against a flat surface, meaning that we only need one radius. All right, number two, it's touching. Okay, how would you categorize this? Okay. Washer method. We do see it touching, but you see there's a gap here, right? It's not up against a flat surface, so we have to subtract out that hole, that gap that's going to be part of our diagram. Okay. Number three, still touching, but number three, still washer, still washer, not up against the flat surface. We need two radius. All right, number four, disc or washer. Washer, it's not even touching, right? So there's an obvious gap here. Washer. Right, so it's important for us to just be able to know what category that we're dealing with before we even begin the problem, because if you miscategorize, then you're going down the wrong track. It's hard to gain a lot of points if you're thinking it's washer, but it's actually disc. All right, so let's go to page 15. I think we went through 1 and 2. On page 15, I want to kind of highlight the steps again before we try the rest of the worksheet. So again, page 15. So what we talked about was that, once we have the shaded region, we look to see where that shaded region is in relation to our axis of revolution. And because the shaded region is completely off and it's not up against the flat surface, we know we have to do two radius, and our radius is going to be drawn, in this case, perpendicular to our axis. So make sure that both radius extends to our shaded region. The big radius is going to extend from dotted line to the furthest boundary, and little radius is going to extend from the axis to the closer of the two boundaries. So once you have your big R and little r showing, it should be obvious which one is big radius, which one is little radius. Big radius is always going to be the one that's longer. Little radius is always going to be the one that's shorter. From here, we look to see where the top and the bottom radius are touching. Here, the top of the radius is touching y=1. Here, the bottom, the big R is touching the -3. So we do top minus bottom, 1 minus -3. That's big radius. Little radius, we look at the top of the little radius is sitting on the curve. The curve is at the equation of root x minus 1. Minus the bottom of the little radius is sitting on the -3. So then we do root x minus 1 minus -3, we get root x plus 2. And our volume formula is very much like how we would if I asked you to find the area between two circles. If I asked you to find the area between two circles, you would just find the radius of the big circle. You would find the radius of the small circle, and then you would subtract them out, right? Big radius, big area of the circle, or big circle minus the little circle, and you're left with the region between. So this is exactly what we're doing, except we're extending it out to a volume formula, but still the same idea, pi, big radius squared, minus pi, little radius squared, and then our bounds from 0 to 4. And the rest goes in our calculator. The more challenging problems, as always, will be the vertical axis of revolution. So if I had a vertical axis of revolution, in this case, revolving around x equals -1. As soon as you see a vertical axis, you know that you have to draw a horizontal radius. If you draw a horizontal radius, you know that the equations that's provided is largely not going to be the way that it needs to be. We have to spend the time to rewrite the equation. That's what makes right minus left a little bit longer to set up. Right? But same idea initially, we start on the axis, we extend to our two boundaries. The one that's moves further away is going to create a longer radius. That's going to be your big radius. Your little radius is going to extend from the dotted line to the closer of the two boundaries. And then we do right minus left. But the right endpoint of my radius is sitting on the curve, and the curve's equation is y equals root x minus 1, but we have to rewrite the equation, solve for x, so I have to subtract 1, square both sides, and get that x in this appropriate form. So every equation that you want to use for right minus left has to start off as x equals. So it used to be x equals the curve in this case. In this case, this is the y-axis, which is x equals 0. We have the vertical axis of revolution, which is x equals -1. So we're using the equations in all the proper forms, and now we can jump into our radius equations. So in this case, right minus left, curve minus the axis. So y plus 1 squared minus -1. And then here, right minus left, the right endpoint of my little radius is sitting on the y-axis, which has an equation of x equals 0. So 0 minus the left endpoint, 0 minus -1. That's the radius. Our bounds, in this case, also has to be adjusted. Look from the lowest to the highest y values. Lowest y value is -1, highest y value is +1. So -1 to 1, big radius squared minus little radius squared. Okay. Practice entering in our calculator, leave the pi out of the calculator. Just attach it at the end. Any questions? So for the rest of the worksheet, there's going to be a mix of disk and washer method. And again, we have to just determine that by looking at the shaded region in relation to the dotted line. Okay. So let's look at number 2. Okay, let the region R be the area enclosed by the function y equals 3 minus x squared. And very clear, but in this diagram, I had this being the x and y axis. So we have the parabola 3 minus x squared. You have the line y equals -2. And then the x and y axis are not the boundaries. They're just there for us to have some idea where our graph is. So our shaded region is going to be this entire portion there. And again, the x and y axis are just there for reference point, but it's not part of our boundaries. And we're going to revolve this region about the line y equals 3. Well, 3 is where the vertex is, so it's going to be touching curve. All right, so the first decision we have to make is it disk or washer method? Washer method, right? It's touching, but it's not a flat surface up against the dotted line, which means that you see all these gaps, right? This gap, we have to make sure we subtract out. Next up, let's build our radius. Our radius will extend from this is, again, I want to keep reminding us that I know the axis looks like the edge of the diagram, but it's actually the center because this shaded region is going to fold over. And it's going to rotate around this dotted line. So it's going to look like a kind of a funny ring-shaped object, but there's not going to be a complete hole in the middle. The middle is going to be slightly touching. All right, so we're going to extend from our axis to our furthest boundary. That I'm going to call big radius. We know we have to go through washer method. There's a gap. So from the axis, I'm going to extend to the closer of the two boundaries. I'll call that little r. Let's see, we do have to find the time or take the time to find the boundaries. Looks like the boundaries are not clear. So we want to set the curve and the line equal to each other to figure out the intersection. So set the parabola equal to the line. So we have our bounds from -√5 to +√5. Big radius. Okay. We know what the big radius is. Big radius is the one that's the longer length. What's the top of big radius sitting on? 3. What's the bottom of big radius sitting on? -3. So 3 minus. Sorry, -2. 3 minus -2. Okay, little radius. Top minus bottom. What's the top of little radius sitting on? 3. What's the bottom of little radius sitting on? It's a curve, right? Especially the curve. Okay. Now I'm going to write this out. See if you can tell me how it looks. There's my top. There's my bottom. Does that look okay? What's wrong with this? Parentheses, right? If I don't set parentheses around my bottom expression, it's going to come out differently. So 3 minus, let's read that negative through, 3 minus 3 plus x squared. Okay. We have our bounds, we have our big R, we have our little r. Now we can just put it into our washer method formula. Pi big radius squared minus little radius squared dx from -√5 to +√5. Okay. Practice entering into your calculator.
Okay, any questions with with 2A? All right, 2B, same shader region. Rotate it about the line y equals -2. For this problem, what's our category there? This, which means that we only need what? One radius, yeah. Okay, so try that, see if you can. A lot of information you can probably carry over from part A. I think I have. Any questions? All right, turn to page 16. You can draw your axis or, yeah, determine where the axis is. Determines washer or disk. Draw your radius. Find your bounds. Okay, let me walk around, see how you guys do with the setup. We're just working through the back of page 16, and that'll be it for today.
Okay, thank you.
That's right. I do show you. Guys, the balance algebraically is gonna be a little harder to do because it's hard to do it by hand. So you're gonna have to go to your calculator and actually find the intersections yourself because if I said natural log of x minus 2 equal to x minus 4, it's hard to isolate x by itself. So we do need to practice finding those intersections. So let me walk you through it. You'll go to y equals. I'll have f of x be the natural log of x minus 2. Now, the natural log of x minus 2, the minus 2 is outside the natural log of x. It's not natural log of parentheses x minus 2. It's natural log of x. And then separately minus 2. So you gotta make sure you close off that parentheses there. So natural log of x. Followed by the x minus 4. I like to do zoom 6, zoom standard, just to see where my graph is. A little small, so I'm going to kind of put a box around this region so I can kind of have an easier time identifying the graphs and the intersection. So I'm going to do zoom 1. I'm going to move to where I think is the upper corner of my shaded region, or of the region that I want to look at. So I'm going to somewhere here. It's a good place, I think. Hit enter. Scroll over to the right. Scroll down till you get that shaded region and that enclosed region in its own. Yeah, easier for you to see. All right, that's better, right? And I can see there's an intersection here. There's an intersection here. So if we do second trace, select intersect. You got to do this twice because I want to find the left intersection, and I also want to find the right intersection. So hit intersect. So first curve, doesn't matter which one you choose. I'm going to choose the one on top first. I want to move close to my first intersection, hit enter. Second curve. Right now, I'm just telling the calculator which curves to consider. And it's going to say guess question mark, hit enter again. And it's going to find that first intersection for me. So 0.158 and negative 3.84. Second intersection. Second trace intersect. Now I want my cursor to be a little closer to my other boundary, other intersection, hit enter. Second curve, enter. So now I should find this intersection for me. It does 3.146, negative 0.853.
Okay, top minus bottom. The top of big radius is sitting on the 2. The bottom of big radius is sitting on the line. So 2 minus parentheses x minus 4. Little radius is 2 minus the curve, so 2 minus parentheses natural log of x minus 2. Clean that up. And I'm just using the x values for the bounds. I wrote down the full order pair because I knew that part B, I was going to have to deal with different bounds because it's going to be rotating around the vertical line. Let me know if you're having any trouble with your calculator finding those intersecting points. Okay, try part B. Okay, part B, disc or washer. Washer. Vertical axis. Right minus left, that means the equation that's provided for us is not in the proper form. I gotta rewrite these equations. Even though it feels easier to just use the original equations, it's not gonna let you set up, you're not gonna do it with the right answer. But you gotta get into, you gotta solve for x. And if your balance has to be adjusted as well. Now, the full order pair that I put down from part A, I can use those because those y values are not now going to be helpful. I'm stacking these circular rings from the lowest to the highest y values.
So I know the equations provided for me, the natural log of x minus 2 and x minus 4 are the ones that I want to use for washer method, but the form is not correct. I have to rewrite the equation. So the y equals x minus 4. I'm going to rewrite it, solve for x equals y plus 4. The natural log of x minus 2 equals y. I'm going to rewrite it to solve for x. I've added 2 to both sides, raise both sides with e as the base to allow that natural log to go away. So now x equals e to the y plus 2. And I have my last equation, which is the axis, which is x equals -1. Okay. My bounds, I've gathered the y values from before. That's going to be proved to be useful. And then we do right minus left for both of our radius. And then we put it into our volume formula. Okay, right minus left, right endpoint of, right endpoint of my big R is sitting on the y plus 4. Right minus left. Right endpoint of my little radius is sitting on the curve, which is the e to the 2 plus y. Okay, 2 more, bottom of page 15. Oh, yes, sorry, they're both negative. Okay, let's finish off with 4A and 4B.
My bounds, one of them is easy to spot. My lowest y value is y equals 2. The highest y value is whatever the intersection is of this curve with this line x equals 4. Well, I know the x value is 4, so if I insert 4 into the curve, I can find the y value. So 4 squared is 16, 16 plus 2 is 18. If I know the x value, I can find the y value at that order pair. Okay, part B, same shaded region revolving around the line x equals 4. Disco washer. What do you guys think? Disk, yeah. There's no, the shaded region is a flat surface against the dotted line, so. Should feel like an easier problem because you already have all the equations from part A. You have the bounds for part A as well. Just have to draw one radius. Okay, any questions? All right, so tomorrow's ACT day. There is going to be a abbreviated schedule in the afternoon, but I'm not going to cover anything new. If any students are here, I'm just going to have you guys practice problems if you want to. So no homework, no nothing new tomorrow. Wednesday we will cover our final topic, which is volume dealing with cross sections. So it's a little bit different, but we're still going to gather information pretty much the same way, just putting into a different formula. And then we can start our test review after that. Our test is going to be next Thursday. All right, can we get your phones?
Sir, I'll be fine. It's like towards with this.
That's. Kids sleep in early. Yes, yeah.
I have.
Yeah.
Another one later? Yeah. Alright, start.
So what you can do is this, you could,
In
you
your-
can curve the line, so we have, y is. Read this one, right?
Yeah.
If you have y, it's equal to natural log of x minus 2, and then you have y equal to or instead they split to each other. But then it's like, well, how do I get there? Okay, so what you do is you just put everything over to one side. So you have natural log of x minus x. So you're gonna go to, edit function. No. Edit function. You're gonna type this in.
Yeah. But that goes into the math.
No.
Oh, so this squared in.
You're excited?
Now, you know that one of the intersection is like it's closer to zero. So maybe we'll start at 0.1 so they can find that bird.
Sydney, you're gonna want to
I
go.
want to go, I just don't remember now, like, I want to, like, but I'm not to miss everything.
Yeah.
Because it's just so annoying, I have to take like 7 emails across the next 3 days. It's like, it's just-
It's not very accurate, right? So we can do it. You go back to the table.
Have you not run over there? I can, it's just like.
Yeah.
You told me like I can run over.
Wait, why?
Going to Puerto Rico and like they're not staying on the resort or anything, but it's like the Airbnb. One of the like surfing town, and so it's like.
Now, you know, there's another one.
So I'm just gonna be like,
Yeah, this is.
on you, like,
This one, maybe.
on the floor.
I've done that before.
Five, so it's probably way past, but it'll, because work backwards and find one set that you want to look for, so.
I think you'll be fine.
There's, when we're in London, there's like a really nice park right next to where it's gonna be so good in the forest. Yeah, I really excited. I am gonna. I'm also stressed because like I can't turn on my phone except for like when it's on Wi-Fi. So it's like,
Oh.
I can only like feel my phone when I get out to the hotel. But then I'm gonna be at the hotel for like
Oh, wait, let's do
for
this.
a couple hours.
Are y'all not, is it just like? You can buy, WhatsApp.
I have that, but so it's like a small thing. So basically,
Oh, was it like this?
no,
It's not
it's.
accurate, but good enough.
Right.
Okay.
Yeah.
I'm going with my old school. My family's chaperoning, so basically we're just going. We're like staying in the same place.
You could buy at the campus first.
We're just